This is the answer to the exercise that I set you on throwing 72 dice. I hope before you look at this you've at least had an attempt to calculate the result yourself. First of all, you're asked to work out the expected number of sixes from throwing 72 dice. Well, the probability of a 6 on each die is 1 out of 6, so the expected number of sixes must just be 72, the number of dice, multiplied by 1/6 the probability for each die, which comes out to be 72 times 1/6 is 12. So we expect 12 sixes every time we throw. Another way of calculating it would be to look at what we said about the properties of the binomial distribution from lecture 2, where for n equals 72 and p equals 1/6 we said that the mean was n times p, which again is 12. So we expect 12 sixes each time. To calculate the mean number of sixes that we actually got in our experiment, you will remember from lecture 1 that to calculate the mean we add up all the values and divide by the number of values. Well, here are the number of sixes that we got from our 9 different throws. If we add those all up, we get a total of 105. So the sum of the values is 105 and the number of values is 9. So the formula says that we divide 105 by 9, which gives 11.666. To 3 significant figures we can round that to 11.7. There's no point in quoting any more than 3 significant figures in an experiment like this. You remember that we expected a mean number of sixes of 12, so our 11.7 isn't very different from that. The third thing was to work out the expected standard deviation. Well, we've already said that each dice had got a probability of 1/6 of giving a 6 and a probability Q 5 out of 6 of not giving a 6. We know that hopefully all the dice are independent and we have 72, n equals 72. The binomial distribution clearly applies in this case. From lecture 2 you will hopefully remember one of the properties of the binomial distribution was that the expected variance is n times p times q. In this case n is 72, p is 1 over 6 and q is 5 over 6. We multiply those together and you get just 10. So the expected variance is 10. We're asked for the standard deviation, which is the square root of the variance. So the expected standard deviation is just the square root of 10, which is 3.2. Now, to calculate the standard deviation from our experiment, in lecture 1 we had this formula: calculate the mean of all the values, subtract the mean from each individual value to give the deviation from the mean, square each deviation, add up all the squared deviations and divide by the number of values. That gives the variance, and then we take the square root of the variance to give the standard deviation. So here are our values. We've already added those up and calculated a mean of 11.7. So the next step is to calculate the deviation from the mean by subtracting the mean of 11.7 from each of the values. 14 minus 11.7 is 2.3. 13 minus 11.7 is 1.3. 8 minus 11.7 is negative, that's minus 3.7, and so on. Then we have to square these deviations. 2.3 squared is 5.29. You'll obviously need a calculator to do that. 1.3 squared is 1.69. Minus 3.7 squared is 13.69, and so on. If we add those all up, then we get 114.01. So the total squared deviation is 114, and the variance is just the average squared deviation. It's 114 divided by the number of measurements, 9. 114 divided by 9 is 12.7. So that's the variance. Now to calculate the standard deviation, we take the square root of the variance. The square root of 12.7 is just 3.6. So that's our answer. The standard deviation of our experimental measurements is 3.6. You might remember that we said the expected standard deviation was 3.2, so our measured value is not very different from that. So I hope you had a go and hopefully succeeded in performing that little calculation. If not, don't worry, we'll get plenty of more opportunities to practice in the future.